Okay, I'm going to start with chapter 15, kinetics of a particle, impulse and momentum. And overall, we're going to look through, sections 1 through 4. So here are the topics for each of the sections. We're going to look basically at the principle behind it. Where does it come from? How can we use it? Just at least some general applications. Then we're actually going to start to apply it in section 15.2 for system of particles. And then we're going to apply this idea of conservation of linear momentum. We're going to define it and apply it for a system of particles. And then we're going to look at impacts, collisions of objects. Okay, so here's an application. What is the basic idea? Basic idea is you apply a force over a very short time interval. Okay, and we want to use this concept to actually, predict some things about the behavior of the system. And it could be, force, distance, time. Those are typical things we might look to solve for, or velocity. Okay. And can you determine the magnitude of the impulse? Okay. Yes, we could. And really, it's a matter. The impulse is going to be that force, or the average force, and the time that the force is being applied to the fender. Okay. Same idea for a hammer striking a nail, right? It's a force applied over a certain amount of time. Short period of time, typically. Okay, here's another one. A force being applied to by the batter or the bat hitting the ball. And is it a vector? Yes, it's a vector. It's going to be a vector in the opposite direction, essentially, of the object that it strikes. Okay. How can we predict the result motion? Okay, so we can apply that. We can use that information to figure out the motion, right? Because there's certain things we want to know. If you know something about this force and impulse that's being applied, you should be able to predict, the direction and the, velocity of the object, right? Okay. Okay. Here's another one. You have a sledgehammer striking a stake. Okay, as it drives it into the ground. If you know something about, like the mass and the initial speed, can you use that to determine the impulsive force, right? Well, it's a matter of if this hammer hits it, what's going to happen? It's going to decelerate over a short distance, right? So you can actually figure out the deceleration, so you could figure out the force if you know knowing the mass and knowing whatever velocity is as it strikes it. So that times over whatever time it takes when it strikes it gives you the impulse, right? So it's that force times that impulse, or the average force. Okay. So then what we're going to do is we're going to look at, the equation of motion, F equals ma, and integrate that with respect to time. And we're going to use that. And that really comes up as the so-called principle of impulse and momentum. All right. And we're going to apply this for, linear motion. Angular motion is in the later sections of this chapter. All right. So here's some things: force, velocity, time. These are things that we can solve for using this. All right. And we'll also look at it when we start talking about impacts or collisions. Okay. Okay. So here's our equation. And we're going to apply this principle of linear impulse and momentum. We're starting off with our equation of motion. So we have the summation of forces equals to mass times acceleration. And we write that a little bit differently. We write it as a dv dt. That is the acceleration. And this is, of course, this is a vector. This is a vector. Okay. Then what we can do is integrate between some limits, both sides. We take dt and put it on the other side of the equation. We're separating those variables. And then we're going to do integrate between two limits. Okay. So between some time period t1 and another time period t2. So this represents essentially the limit of the time, right? So you're applying some force between t1 and t2. And you have some initial velocity at that time when that force was applied. And then you have some final velocity at t2. Okay. So the result becomes essentially, this is the impulse and the momentum on the this side of the equation, right? All right. Okay. So just formalizing this. The mv, vector mass times velocity, is called the linear momentum. Okay. And basic idea is the vector has the same direction as v, which makes sense. The linear momentum vector has units of this. Kilograms dot meter times meters divided by seconds, or of course in the USCS system. So this is SI, this is USCS. Okay. And then the other side of the equation, the integral, the force integral with respect to time, is the linear impulse. Okay. And it's a vector quantity, of course, and it acts in the same direction as the force. Right? And it has units of Newton seconds or pound seconds, basically force and time, right? And that's denoted with I. And so when you see this in equations, essentially it's just this integral, all right? Okay. And of course, this is just the impulse can be determined by direct integration. So it's just the area under the force curve between the two times, right? Now, of course, if this was constant, right, if the force curve was constant over that period of time, it would just be the force, that value of the force, times the difference between the two times, okay? So it simplifies to this. So in certain cases, you can use this. So the principle of linear momentum, linear impulse and momentum in vector form can be written like this. And really it's just taking this term from the right-hand side and putting it on the left-hand side, okay? What does it mean? Particle's initial momentum, that's this, plus the sum of all the impulses applied. So this is summation of all these. So it could be more than one force, of course, from T1 to T2 is equal to the particle's final momentum, okay? And you can actually, so you could use an impulse diagram for this, okay? So what do you have? You have some initial momentum, impulse diagram, so here's the impulse, and then the final momentum diagram, okay? Okay, so if we're resolving it, our vector into x, y, and z components, you can actually just set these equations up as the scalar components individually, right? So in each direction. So what you'll find is, the vector form is valid, of course. The individual components, and if you want to think about, the three unit vectors or the directions I, j, and k for these, is that the individual scalar equations also are valid, okay? So we could represent it this way, if it's just the x components, the y components, and the z components, okay? So it may be that, this is more convenient to do this and simpler to go and solve the individual components as opposed to setting it all up in a vector form, okay? And that's if we're using Cartesian coordinates to represent it, right? Okay, so for problem solving, and let's say we're doing it, Cartesian coordinate system, we're going to establish the coordinate system and then draw the free body diagram, establish particles' initial and final velocities, and drawing the impulse and momentum diagrams for the particles. So we draw the diagrams as needed. Then we break it up to the components, okay? And then perform, integration as needed to get the impulses, individual impulses, okay? Okay, so we'll look at an example. And we have a 0.5 kilogram ball, strikes a rough ground, and rebounds with velocity shown, okay? Neglect the ball's weight during the time it impacts the ground. Okay, so the assumption here is that, the force due to the ball's weight is going to be very small compared to the force or the deceleration force here, okay? So the magnitude of the impulse force exerted on the ball. Okay, so we're looking for that impulse force. All right. So we're going to draw the diagrams first, momentum and impulse diagrams as it hits the surface, then apply, of course, the principle of impulse and momentum, determine the impulsive force. Okay, so here's the diagrams, right? So here's our first diagram, our momentum. Here's our impulse, and then our final momentum. Okay, so here's the direction defined. Here's our weight. Well, we say the weight. We're kind of ignoring that, right? So we're saying the weight's 0, of course. Then the normal force is 0 due to that. Okay. So the impulse being, the ground applying back on it, the force of the ground against the ball. Okay, so that's that. Okay, so then we go and apply principle of impulse and momentum. All right. So this one, here's our equation. You have some initial momentum associated with it. And of a lot, here's your momentum. You have a mass times its velocity initially. So we're given that information. And then we want to know the summation of the forces over this time period, the force that's applied. So this is kind of what we're trying to figure out, the impulse, because this is the impulse, right? Equals to mass times the final velocity, okay? All right. So first thing we do is we break it up into its components, okay? So the 0.5 is the mass, the 25 is the velocity, okay? And here's the x component of the velocity. Here's the y component of the velocity. So the directions, it's going off into the positive x direction. It's going into the negative y direction here, right? The 25 meters per second for that, the ball. So it's going off the negative y direction. So that's equal to, here's my impulse, right? Okay. So, so this is the final one. Sorry, this is the impulse. This is our momentum, initial momentum over here, and this is our final momentum here, right on the right-hand side of the. This is the right-hand side of the equation. 0.5, of course, the mass is the same, and we have our final velocity, which is the 10 meters per second, and then the angle now, of course, is 30 degrees. So now we have. Here's our x component of the momentum, and here's our y component, right? And they're both positive, right? This is basically reverse direction. Okay. So now what we have for the impulse force vector, of course, is just this term. So we don't know necessarily how much time it struck the ground for, and we don't know how much of the component is the force. We just know the impulse, right? We can only solve for the impulse at this point. Okay, so here's the vector, which essentially is just these components, right? So we took this part and added it to this on the other side of the equation, or subtracted it out from this on this side of the equation. Okay, and then you come up with 4.509 and 11.34 Newton seconds. So here's the impulse, and then here's the magnitude, right? Take the x and y components, and you have the magnitude of that force. Okay. And here's, of course, the direction, or the magnitude. I shouldn't say the force. It should hit impulse, the magnitude of the impulse, right? Because it has both. It has also multiplied times time. So here is our x component and our y component of the impulse, right? So the only thing you know about it is that it's a force over time. And it's this much time. If you wanted to think about it, it could be, it's 12.2 seconds, 12.2 newtons in 1 second, or 122 newtons in 0.1 seconds. There could be just an infinite number of possibilities for this, right? Without any more information, that's really all we can say. Okay. Okay. Here's the second example. Okay. So just looking at this example, so we're given a diagram represents basically traction force or over some period of time, right? So what is this? If we find the area under this curve, we have the impulse, okay? And of course, here's the time given. This is, the speed of the car when t equals 5 seconds, okay? So we're given some information here. We have some uh, initial momentum, let's say, and some final momentum that we can calculate. So, this is another impulse and momentum type of a problem, okay? So here's our plan. Draw the momentum and impulse diagrams of the car and apply the principle of impulse momentum to determine the speed. Okay, so here's our diagrams, right? So we have some initial momentum, which in this case, it was 0. So it started off at 0, had no momentum. An impulse was applied over some period of time, which was over 6 seconds. And the impulse, we need to find the impulse from the force graph and, the force graph plus additional components here, right? We have the weight and normal force. And at least that's part of our diagram. And that'll give us some final momentum. And a couple of points here from the diagram, right? Even though you drew this originally, you might have recognized that these could be canceled out, right? Because if you broke it up into x and y components, what you'd find is that here's your x essentially, and this is the y. Well, you have one force acting down, one force acting up. These two, of course, are going to cancel each other out, okay? So you'd have, whatever impulse is due to this force, this times time, and this times time, so just the negative of it, so these would cancel each other out, okay? The second part is, or just thinking about this, the force. Why is it drawn to the right? Well, it's a force against of the wheels against the road, which is pushing off to the right? The traction of the road, okay? Which should make sense, because if you had drawn it the wrong direction, it would essentially mean it's going in the opposite direction, okay? And that's kind of the main points here. Okay, so here's the equation and impulse and momentum. And of course, it's applied in the direction of motion. And that's all we really have, is just essentially, the x component of it, okay? Well, we know this was 0. And this represents essentially the area under that curve. So if we come up with the area under the curve, we now have the impulse. And we know what the mass is, so the last thing to solve for is just v, okay? So here's the area under the curve, which is just, of course, here's our original one, right? The 1,500 kilograms. This is our momentum, initial momentum, which is 0, because there's no velocity. And then, of course, this is just 6 k-newtons times 2 times 0.5, because it's just going to be half the area, right, under this curve. And then the second part of this is from 2 to 6 seconds, which is just 4. And it's constant force, right? So I could just multiply the force times the times difference. And that's going to give us our momentum at the end, right? Our mass times our velocity, okay? So you can easily solve for velocity from this. Just divide the left-hand side by 1,500 kilograms, okay? All right. So for the next problem, what we have is we have a crate moving downward, and then the motor, at some point, pulls on the cable with a force F, okay? And it pulls for a certain amount of time, and this one's equal to 6 seconds. So it's an impulse basically between time t equal to 0 to 6 seconds, okay? So we're going to go and draw the momentum and impulse diagrams of the crate and apply the principle of impulse and momentum to determine the speed, okay? Okay. So first thing is, we're going to actually go and do the momentum and impulse diagrams for the final momentum diagram. And you'll notice here that it's 2 times F, okay? And that, of course, is due to this. You notice that there's a tension here and a tension here, right? And since it's the same cable, it's F here and F here, right? So it's the same tension pulling up. So it's double it. And the distance, of course, is half that it's going to travel, but the force is double, okay? Double the tension. So that's the 2F going up. And here's the weight going down. And then that's going to equal to our final momentum, okay? So here we go. Here's the first part of this part, Okay, the impulse due to this force being applied for 6 seconds. Okay, so you can solve that. Just do the simple integral here for the function. And you could do an integral. You just think about what's the area here, right? You could just do 150 times 6 plus half of this one, right? Half of 450 minus 150 or 300. Okay. So this one they chose to do it as like 0.5, half of the two added together. Okay. So it depends upon how you want to look at it. But the end result is the 3600 Newton second. Okay. And then the second part of this is the weight, right? And it's negative because it's going down. And this one is just, it's just going to be, it's constant force, right? So it's just here's the weight, mass times the gravitational acceleration times 6. And here is the impulse in the other direction. Okay. Okay. So all we have to do is go and apply this impulse and momentum to determine the velocity. Okay. So here's our initial one, right? So the initial one said it was going down. That's why you have your negative. Here's my mass times the initial velocity. And here's the due to the weight, the impulse due to the weight. And here's the impulse due to the motor pulling it up. And that's going to give you essentially the mass times the final velocity. So you just go through and solve it, and you come up with velocity 21.1 meters per second. Okay. That's